My name is Haiyang. I currently work at Uppsala University in Sweden. Exactly 10 years ago, I started my PhD work at NTNU with Zhiliang and Jianying. So since then, we have been working together trying to develop mechanism-based predictive models for hydrogen embrittlement. And in short, today I'm here trying to sell to you our new perspective of interpreting hydrogen-induced decohesion, which rules in plasticity and the void process. Our vision is really to develop a mechanism-based model, which is capable of capturing both the macroscopic and the microscopic features of hydrogen embrittlement. The model should be able not only to capture this reduction in global strength and ductility, but also be able to capture the change in microstructural features on the fracture surface. When there's no hydrogen, we have dimpled fracture surface, which is typical of ductile fracture. And when there is hydrogen, the fracture surface will look relatively featureless and brittle-like. Of course, if we examine it under high resolution, we observe lots of tiny dimples. But in my time, when doing the PhD, these experimental evidences are not widely reported or discussed. So I mainly focused on cohesive sound modeling of hydrogen embrittlement, assuming that it's mainly about hydrogen-induced decohesion, aligning with the heat mechanism. I think we are all familiar with the cohesive sound model, so I won't waste more time elaborating this one. But basically, the cohesive sound model starts from the brittle side. It wants to simulate the brittle fracture induced by hydrogen, and it attempted to include the ductile fracture. I mean, by changing the cohesive parameters, we are able to capture the global reduction due to hydrogen, which could include ductile fracture. However, it's very challenging to capture the ductile fractography with cohesive sound model because it lacks an inherent connection to voids or to microscopic plasticity. So this could be the limitations of the cohesive sound model. Like all the other models, every model has its limitation. And speaking of ductile fracture, it's well established that this fracture is explained by the microvoid process. We begin with pre-existing or nucleated microvoids, and the voids will grow under loading. When the voids link up or when they coalesce, there will form a crack, meaning fracture. With the classical unit cell approach, which is essentially a void containing representative volume elements, it's possible to simulate the ductile failure process. And by considering the influence of hydrogen on plasticity in the matrix, it's then possible to incorporate the hydrogen effect. And actually, as pioneered by Professor Sofroni's group, with this method, it's possible to capture the global reduction in strength and ductility when there is hydrogen. In our work, we found that if we really combine the cohesive sound model and this unit cell model, it's possible then to capture not only the reduction in strength, but also the change in fractography. Imagine that if we insert a layer of cohesive elements at the void ligament, then we have the possibility to separate the void ligament before the voids grow to be very large. In that way, the fracture surface will be featured by a relatively flat decohesion ligament with small voids. Then we could produce this brittle fractography with the small voids. We actually practiced this idea using a so-called Gerson model, which is a well-established model to model void-based fracture mechanism. And the version we utilized is the model proposed by Zhiliang, the so-called complete Gerson model. This model detects failure by tracking the maximum principal stress in the material point. So when the critical principal stress is reached, we observe the failure. As you can tell, this approach has a link with the cohesive zone model, which is also based on fracture energy and maximum fracture stress. So if we apply a similar hydrogen degradation law, which was applied to the cohesive zone model, we have a possibility to consider this kind of a decohesion failure in the complete Gerson model. Therefore, with this platform, we managed to capture not only the reduction in the global strength and ductility, but also a change from ductile fracture to brittle fracture. And it should be noted that here, with this model, we started from the ductile side and we managed to proceed to the brittle side. But this was the work we did 2 years ago, and it was also presented at ECF 23. But we have to say that this work is not completely satisfactory because still a phenomenological hydrogen degradation law is needed. And with this law, although we have combined decohesion and void mechanisms, but the physical basis is not consistent because we still need to introduce decohesion. So in the past 2 years, we have tried to develop a model which is more consistently based solely on the void process for hydrogen-induced decohesion. And we were inspired by recent experimental evidence on this microvoid or nanovoid processes in hydrogen-induced fracture. For example, here we have microvoid formation due to hydrogen-promoted particle debonding. Here we have nanovoids due to perhaps plastic localization and vacancy condensation. And here, most recently with X-ray imaging, nanovoids were found to contribute or even dominant in intergranular fracture induced by hydrogen. Then our idea is if we have this hydrogen fracture process zone, which is able to capture all these processes based on the secondary small voids, we might be able to process decohesion. So our model is simply like this. We have the pre-existing primary voids, which would be responsible for the ductile fracture if we don't have the damaged processes in between. But now with hydrogen, due to HELP and due to PASIVE, we could produce lots of secondary small voids in between. And these small voids could eventually dominate over the primary voids, and they will be responsible for fracture. And when they process fracture, as we see here, the primary voids will not grow substantially, and we will have very small, tiny voids decorating the brittle-like fracture surface. And what is more, when we have this kind of a fracture process zone, the size, as you see here, will be very limited, within perhaps hundreds of nanometers. That means when we observe the fracture surface microscopically, it's perfectly brittle. So based on this idea, we developed this void-based decohesion mechanism. And as mentioned, this mechanism could enable a link to the microstructure, to the plasticity, and more importantly, or equally importantly, it is consistently based on the void process. So in order to practice this idea, we utilize the classical unit cell approach with a single primary void, as shown earlier. But now we have inserted a confined, extremely confined hydrogen process zone between the two primary voids. And in this process zone, we had the tiny small secondary voids, and now we idealize them as an array of equally spaced uniform secondary void array. And in this array, we are able to characterize this secondary voids just with two parameters. I call the first parameter as a void size parameter. It is a ratio between the void radius or diameter and their spacing. Okay, with this one, we know the size of a void as long as we are given the dimension of this green box. The second is the void number parameter. So with this parameter, because the interligament length, the total length is fixed. So this parameter actually decides the size, determines the size of this green box. And it actually determines the thickness of the process zone. So as the number reaches infinity, we have an infinitely thin process zone, which makes it possible to capture the entire range of hydrogen embrittlement. So starting with the case without secondary voids, the number is 0. We have the classical ductile fracture, which is already well solved. When we have a few secondary voids, which is this case, the secondary voids may interact with the primary void and promote ductile fracture. This is what we observe at the, if you remember, a S-curve depicting hydrogen embrittlement. So when the voids becomes more and more and smaller, the secondary voids will take over and they will dominate the fracture process. Then the fracture surface will be decorated with extremely small voids produced by this process. And when we approach infinity, there's no voids anymore. It reaches equation because now our fracture process zone will become infinitely thin. It will separate in a brittle manner. Here I show that, gradually increasing hydrogen concentration and the number of secondary voids, gradually it becomes more and more brittle. So with this unit cell approach, we did perform simulations trying to show that we can capture both the macroscopic and the microscopic changes. So first, by increasing the number of secondary voids from 0 to a large number in the ligament, we can really observe the reduction in strength and ductility, which shows that, yes, we are really getting a more and more brittle behavior if we have hydrogen. And what is more interesting, as we are increasing the total number of these secondary voids, because we are fixing the void size parameter constant, the result is that we are actually having smaller and smaller void volume fraction. This is something actually surprising because according to the classical theory, the smaller the void volume fraction, the more ductile the material is. However, we show that with this voids, when it becomes smaller, we can really get more brittle behavior. And this is the last slide of my results. With this one, I show that the model or the rationale is able to capture the microscopic fracture mode transition. When there's no hydrogen, again, we have the classical large void fracture, which gives us large dimples on the fracture surface. But when we have secondary voids, as you can see, fracture is processed by secondary voids without enlarging the primary voids. So we really are getting this more brittle fracture surface decorated with small, tiny dimples. Yes, I think I will stop here. And this is our take-home messages for you. Perhaps you can read it by yourselves. But basically, I want to say that in a humble way. If you can manage the void nucleation, I mean, if you can characterize them, then perhaps we could help to manage the rest of the embrittlement. Thank you very much.